Bismillahirrahmanirrahim. In this lecture, we will start with chapter number 1. The title of chapter number 1 is Semiconductor Diodes. Right, now we come to the sixth slide. In a pure silicon or germanium crystal, the four valence electrons of one atom form a bonding arrangement with four adjoining atoms as shown in figure 1.4. Figure 1.4, we see a number of only silicon atoms which are sharing their electrons with adjacent atoms only for one purpose, so that their outermost valence shell can be complete. Now, this arrangement that you see is called the crystal. It is called the single crystal of silicon because we see no other atom or we see no other element besides silicon. Now, this sharing of electron, this phenomena is the covalent bonding. This which I've highlighted with red color. This sharing of electron is called the covalent bond, and the definition is this bonding of atoms strengthened by sharing of electron is called covalent bonding. So figure 1.4 demonstrate the intrinsic silicon crystal where the silicon reacts with other silicon atoms to share electrons and complete its octave. And as a result, what do we get? What do we get when we get sharing of electrons? The valence shell is complete. In addition, the interaction of atoms will be strengthened. Now, just as
Excuse
a
me, sir.
small teaser, what will happen if I remove the center atom? What will happen to the crystal? What will be the impact of removing the center atom of silicon? So the four adjoining atoms will be influenced. So all of these four silicons, they will be affected. And then these four silicon atoms, they would welcome any other atom that would share the electron only for one purpose, that the crystal becomes stable in terms of valence shell. And we will take advantage of this case, that where we intentionally remove one silicon atom and replace it by another element, and this other element, which process is called doping, will create either a p-type material or a n-type material, and this we will see in a later slide, inshallah. Now we see the case for gallium arsenide, and since gallium arsenide is a compound semiconductor, there is sharing between two different atoms. Two different atoms means the two different elements, as shown in figure 1.5. Each atom, gallium or arsenic, is surrounded by atoms of complementary type. In this compound, we only find two elements. One is the gallium and second is the arsenic. We will not find two gallium interacting with each other until there is one arsenic in between. So if we look closer to the atomic arrangement, for example, here we see one arsenic atom which is interacting with two gallium atoms. Likewise, this gallium atom is interacting with three arsenic atoms. So the word complementary means that first we will have one atom of one element, adjacent to it is the atom of the other element, and this process will then repeat itself. So this is the complementary type. After gallium, arsenic. After arsenic, there is gallium. Okay, there is still a sharing of electron similar in structure to that of germanium and silicon, but now 5 electrons are provided by arsenic atom and 3 by gallium atom. Gallium is sharing 3 electrons, whereas arsenic is sharing 5 electrons. And as a result, after this sharing, the outermost octave of each atom, either gallium or arsenic, is then complete. Next slide. This is an important note in the case of gallium. Although the covalent bond will result in a stronger bond between valence shell and their parent atom, it is still possible for valence electron to absorb sufficient kinetic energy from external natural cases to break the covalent bond and assume the free state. Free state means that the electron that although we have a very strong covalent bond, but even then if we apply some energy from external energy, then the atoms residing in the valence shell, they can still absorb energy, kinetic energy, and then move or jump into the conduction shell. And this is called the free state, where the electron becomes a property of any atom. The term free is applied that has separated from the fixed lattice structure and is very sensitive to any applied electric field, such as established by voltage sources or any difference in potential. In fact, this is the process how we get current, that we apply external EMF, electromotive force. The electron, they absorb energy and hence they move from the valence shell to the conduction shell, and then they start conduction. Conducting electron is called your current. And what is the nature of external sources? They can be light also. We have compound absorb light energy, and the electron, they become free from the covalent shell. Right. The external causes include effects such as light energy in the form of photons and thermal energy from the surrounding medium. At room temperature, there are approximately 1.5 to the power 10 free carriers in 1 centimeter cube of intrinsic silicon material. That is 15 billion electrons in 1 centimeter cube. So this diagram shows how light can cause electrons to jump from the valence shell into the conduction shell. Right, after the covalent bonding comes the intrinsic material. Intrinsic material is semiconductor material. We have removed the impurities and essentially as pure as can be made available through modern technology. We cannot get 100% intrinsic material. Further onward, the free electrons in a material due only to external causes is referred as intrinsic carriers. The free electron in a material due only to external causes are referred to as intrinsic carriers. So this was the intrinsic carriers. Okay, now table number 1.1 compares the number of intrinsic carrier per cube centimeter for germanium, silicon and gallium arsenide. Gallium arsenide intrinsic carriers are 1.7 to the power 6. In silicon there are 1.5 to the power 10, and for germanium there are 2.5 to the power 13. So what do we learn from this table, by the way? So we have gallium arsenide producing 1.7 to the power 6 intrinsic carriers as compared to germanium producing 2.5 to the power 13 intrinsic carriers. So which one is better?
Gallium arsenide, because it is more close to semiconductor behavior.
Yes, please everybody carefully listen that in this table we see three semiconductors: gallium arsenide, then silicon, and then germanium. Gallium arsenide has the least intrinsic carriers. Germanium has the maximum intrinsic carrier. This means that germanium is the poorest. It is the least considerable. It is the least preferable because when light falls on gallium, I'm giving an example only. When light falls on gallium, the gallium will release 2.5 to the power 13 intrinsic carriers, which is not good, by the way. We don't like such material that on which light falls and it starts releasing intrinsic. So this is happening without our control. However, if we have gallium arsenide, when light falls on gallium arsenide, it will release 1.7 to the power 6 intrinsic carrier, which is much smaller, and it is much more preferable than gallium. So let us look at the table 1.1 again. We have external sources influencing our intrinsic material. If this diagram represents gallium arsenide, then the gallium arsenide releases 1.7 to the power 6 intrinsic carriers. If the material was germanium, the germanium would release 2.5 to the power 13 intrinsic carriers. Now which one is better? we would prefer gallium arsenide. But what if our application is to produce intrinsic carriers? For example, your photo cells, for example, solar cells. So naturally we would use germanium. Now we come to the 11th slide. Now here is the relative mobility. Relative mobility of free carriers in material, that is the ability of free carriers to move throughout the material. How easily the carrier they can move within the material, not out of the material. How easily the carrier, for example electron, they can move within the material. This is called relative mobility, and the unit is centimeter square per volt dot second. In the case of silicon, the relative mobility is 1500. In the case of germanium, it is 3900. In the case of gallium arsenide, it is 8500. Table 1.2 shows that in the case of silicon, the relative mobility is 1500 centimeter square per volt per second. So the electron have a relative mobility of 1500, whereas in the case of gallium arsenide the relative mobility is 8500 centimeter square per volt per second. Looking at this table, atoms in gallium, they face maximum difficulty in crossing the material, whereas electrons in gallium arsenide, they face the easiest movement for moving through the material. It is due to this table that our very large scale VLSI circuits, they are built on gallium arsenide, because gallium arsenide offers the maximum relative mobility. So table 1.2 shows that free carriers in gallium arsenide have more than 5 times the mobility of free carriers in silicon, a factor that results in responsive times using gallium arsenide electronic devices that can be up to 5 times those of the same device made from silicon. So for very high speed electronics, we would definitely prefer gallium arsenide.
Sir, what is the effect of temperature on mobility, relative mobility?
Well, every semiconductor has a negative temperature coefficient. This means that as temperature increases, we will get more and more carriers. These carriers, they will produce more and more I square R losses. Carriers are charges, moving charges is called current. As the current moves, it produces more and more I square R losses. This I square R losses then further increases the temperature of the semiconductor. Semiconductor will then release more free electrons or more carriers. The temperature coefficient is negative, and hence our electronics, they burn out. We see that our electronics, they burn out due to this runaway effect, that as temperature increases we get more free carriers. These free carriers, they produce more I square R losses. If our heat sink is small, then heat cannot be extracted. This heat will be contained within the material, and hence we will get a burnt out material. Plus we need a proper heat sinks. Therefore, if we open your laptop, look inside the microprocessor, you will always find that the microprocessor, although it is made up of gallium arsenide for relatively large mobility, plus there is a heat sink, and this heat sink is extracting the heat.
Sir, suppose if we increase temperature by 20 degree for both silicon, germanium, and gallium arsenide, then which material relative mobility will increase heavily?
Well, this we will postpone this answer when we come to Fermi levels, where this answer will be dealt in detail. Keeping in view the formula, of the Fermi levels, the internal structure or the activity is going inside semiconductors.
Okay,
Right,
sir.
next we come to energy level. This is article number 1.4, energy levels. energy levels are the energies of each shell, and one electron must acquire certain amount of energy level to jump from one shell to another shell. So the further electron is from the nucleus, the higher is the energy state. Any electron that is left its parent atom has a higher energy state than any atom, any electron in the atomic structure. So here we have the nucleus over here, and then there are shells. Each shell has energy levels. ये जो energy levels है इनको आप measure किस में करेंगे? In terms of electron volt, and this energy level is important because it defines the very nature of the material. The insulator, the conductor, the semiconductor, they are all differently classified depending on their energy level. Therefore, if we look at the insulator carries the largest energy gap between the valence shell and conduction band. So one electron residing in the valence shell of an insulator, it requires largest electron volt to jump into the conduction band. However, if we look at the conductor case, where the valence shell and the conduction shell, or the valence band and the conduction band, located very close to each other, and in some cases they are also overlapping. Therefore, they require very small amount of energy. Even our normal room temperature would be enough to push the electrons from the valence shell to the conduction shell in conductor case. Now, in the third case, we have the semiconductor. The semiconductor, the energy gap is medium. The valence shell and conduction shell, they are not overlapping. There is a energy gap existing between them, but this is not large as compared to insulator. And then when we provide certain electron volt, the electron, they will jump from the valence shell to the conduction shell. And this applied electron volt is different for germanium, it is different from silicon, and it's different for gallium arsenide. In the case of germanium, it is 1.6 electron volt. Then for case of silicon, it is 1.1 electron volt. And in the case of gallium arsenide, it is 1.4 electron volt. So the last slide is that the electron volt measured as EV is volt VQ, or electron volt, that is equal to 1.6 to the power minus 19 joules. So 1 electron volt is equal to 1.6 to the power minus 19 joules. So this brings us to the end of our lecture. So please everybody, all the class, all my students, please read from the textbook. Inshallah, next time we will start from article 1.5. Thank you very much.